Hello and welcome to the Aether Techinar. Thank you for joining us today. Now I'd like to introduce our speaker for today, Larry Peterson. Larry is ONF's Chief Scientist and Chair of the Aether TST. Larry?
Thanks, Denise, and welcome everybody. So today I'm going to give you an update on what we've been doing recently with Aether. I thought I would start with a little background information for those of you that this might be new, but even if you're familiar with Aether, I think a little context as to how Aether got started and what was important to Aether will help explain what we're doing in the transition that we're taking right now. So, let me see here. So what I wanted to start with is the project that basically funded all of the Aether development. That was the Pronto research project funded by DARPA. It was involved universities, Stanford, Cornell, and Princeton, plus ONF was the main engineering arm of the project and did most of the engineering work. And the title of that was to secure the internet using verifiable closed-loop control. The objective of Pronto was to create and deploy the world's first, excuse me for a moment as I adjust my screen, first network, including 5G, under verifiable closed-loop control. So closing the loop, control loop of the network, including 5G, was a major objective of the work. And it was also an important objective that Pronto be an operational network that is deployed in a production environment, carries real traffic, and runs innovative edge services. So this is all important because it shapes what we ended up doing with Pronto and with Aether. So the approach that Pronto took as the umbrella project had a research component. It had and there was a lot of AI and using for control loops and real-time closed loop control and detecting attacks of various kinds. And there was an element of formal verification of the data plane that was programmed in P4. So that was just a very quick summary of the research agenda. There was a very substantial development aspect, and that was to build Aether, an edge cloud with software-defined core, software-defined RAN, and software-defined switching fabric. P4 was an important part of that. And the third leg of the project was to actually operate this network. So we wanted to deploy it, operate private 5G at the universities that were participating, ONF, Intel, and elsewhere as well. And this led to a virtuous cycle that the research influenced what we built influenced the research, and certainly the experience we gained operating this network contributed both to the research and the development. So this is just a bit of background to help you understand what was important and what got built as part of Aether. I'm going to focus mostly on Aether, but I did just want to just put one slide up, a couple of slides up. This will be really quick, just to take you back 3 years ago when the Pronto/Aether project got started. We were just at the point of transitioning from 4G to 5G. And what, of course, we all recognized was that disaggregation was going to be an important part of that. Disaggregation had always been central to ONF's missions as all the SDN work happened there. But what we saw was an opportunity for both open source, cloud native, and SDN principles to be applied end to end across this entire data path. And in fact, that end-to-endness of making it programmable end-to-end was a central part of the story. And so in the RAN case in particular, we lifted the control plane out of the central unit and elevated it into an SDN-like controller and built a set of control apps on top of that. That, of course, is the near real-time RIC that has become a central part of 5G redesign, but that was certainly front and foremost as we got started with Aether. Then, of course, there's a management plane on top of that. The big takeaway, though, was this now gave us the opportunity to have control loops at 3 different levels of granularity. And it was important to Aether to expose all of those levels of all of those control loops. All right, so that's just a little bit of a background that motivated us. This did lead to an operational deployment that has been running for several years now. It was all the participating universities, a couple other sites. There was a central cloud managed component to it that ran in the Google Cloud. And of particular note, and I'll come back to this a little bit, there was the first disaggregated 5G field trial done in collaboration with DT and several other partners that was part of this. It was a demonstration of all the technology we developed actually running in real-world field trial in Berlin. Okay, so that's the Pronto project, of which Aether was an important part. And if you're watching closely, you'll see that I first started talking about Aether as a managed cloud service, which it is. It is also, however, an open source private 5G platform. So I'm using the word platform now in the sense that it's something that you can download and you can stand up your own version of Aether. And that's really what where the transition that's underway right now is happening. So start to think now in terms of software components. There's an SD-RAN, there's an SD core. It has a user plane piece and a control plane piece. There are edge apps, there are central apps, and there's a control and management platform. One of the key important objectives of Aether was that we be able to do local breakout, and so that you could, without leaving the enterprise or leaving the premises, you could communicate between the small cells that were distributed throughout your physical plant and the edge apps. The core's control plane ran in the central cloud, and the management platform ran in the central cloud as well. So this is a high-level view of what the objective was. If we sort of start at the bottom and work our way up, we started with commodity hardware, commodity servers, obviously, but also we started out with P4 programmable switches. That's no longer a requirement, but that was part of the original design. To turn that hardware into a platform, of course, and then we also were attaching 5G small cells, excuse me. To turn that into a platform, there are two pieces. One, we use Kubernetes to control the workload of the jobs that got to run both on the switches and on the servers. And we put an SDN-based switching fabric in place. So that is what we consider to be the Aether platform. On top of that platform, then we were able to run the connectivity workloads, which includes the user plane of the core and the SD-RAN. Now, those are just Kubernetes workloads. All of that then constitutes what runs at one edge, which we call the Aether connected edge. There were multiple of those, as you recall back to the picture from a few minutes ago. And in the central cloud, we ran multiple instances of the control plane. And that's where the Aether management platform, which we also call AMP, runs. That's the cloud management aspect of Aether. So those are all the parts, and that's kind of the architecture diagram, if you think in terms of the key subsystems of Aether, running both at the edge and centrally. So what I'm going to do in a few slides is give you a little bit more detail about each one of those subsystems, and then we'll come back and talk in a little bit more depth about some key aspects of the management platform. So SD core, the control plane. There's both a 5G version of the control plane and a 4G version of the control plane. They share a common data plane or user plane, a UPF function that was both speaking N3 to 5G and speaking S1U to 4G. The focusing now more on the 5G aspect of it, the next generation core was microservice based. Now, I'm not showing you here, but this serves then as the foundation for scaling out, for example, the AMF. So there's research going on that scales up the AMF. There's other people working on scaling up the SMF. There are people working on multiple slices, each being served by a different UPF and so on. So that's the core. The RAN, again, is SDN based. Remember the animation from a few minutes ago. It includes both the E2, the ORAN defined E2 interface to the networking elements. It is built from a set of microservices that were available to us because we had already built ONOS as an SDN controller for the fixed line. Now we've just augmented it and reused a whole bunch of parts to build a non-real-time REC. And I think the other main takeaway here is that it does support the ORAN the two ORAN service models you see there. So again, it's a Kubernetes workload loaded onto the Aether platform. Just a quick, very busy picture. Apologize for that, but these components that I just described very briefly were included in that Berlin Open RAN field trial. So the core was there, both the 4G and 5G core. The UPF was there. There was actually both a microservice-based version and a P4 version that ran in the switching fabric. The switching SD fabric is a component of this diagram. And SD-RAN is there, and it ran both some example control apps that we built and some example control apps that others had built. And it was running primarily on a set of Radis's components out in the disaggregated RAN. So this ran for a couple of years, sort of just to emphasize the point that it's ORAN, it's based on the ORAN or compliant with the ORAN architecture, and actually was able to run in field trials. So pulling back from those two main components, SD-RAN and SD-Core, let's look at this bigger picture for a moment and focus now on the Aether management platform, which is how we turn all those components into a cloud service, a centrally managed cloud service. So it basically consists of 4 components: monitoring, logging, runtime control, lifecycle management, and provisioning. So I'm just going to give you a quick look at each one of those, starting with monitoring and logging. You may recognize this. It's because it's based upon open source. So everything we did here in AMP is based on open source: Prometheus, Grafana, Elastic Stack, and so on. We monitor both the health of the servers and so on, but also built metrics to monitor the behavior of the SD core, for example, how the UPF is performing. The second piece of AMP is the runtime control API. This is a programmatic API that we generated, that we defined, and were able to generate from a set of specs that manages devices, allows you to aggregate devices together, isolate traffic into slices, connect device groups to applications, set the QoS parameters on those slices, connecting the applications to the devices, and so on. There's a GUI that's associated with that. There's nothing wonderful about the GUI. It's basically a straight GUI front end to that API. The thing I want to emphasize here, though, is this is an important aspect of what Aether is about, and that is it's not just the software components, but it was an attempt to build an API that lets you do closed loop control on those components, and that's an important part of what is going to go forward with Aether. So if you take those two components together, we basically now have the ability to build closed loop control applications, watch what's going on, and make control operations to change it. And just as an example of that, one of the demos that we did, and this is now a demo that was done for DARPA, takes basically the Aether deployment, an Aether Edge, just like I've described before. And it was a set of drones that were flying information, and the local application is running at the edge. It's not going to work if it's running far away. So the time delay here is an important aspect of this. There happened to also be a motion capture local app. It was wired to cameras, so that part of it was not using 5G, but the drone control is communicating with these drones over 5G, and we get the closed loop control out of it. And I'm not going to go through the details of that, but there were various attacks and things that happened that you recognized, and then you closed the loop on it. Okay, so that's runtime control and monitoring and logging. Those are critical aspects of Aether. What I want to focus now is more about what's changing and the reason we're doing this webinar in the first place, which is related to lifecycle management. And this is from the start, we had an objective of continuous integration, continuous deployment. We would check code in that made, evolve the core, evolve the RAN. It would be integrated and tested. And I've simplified the diagram here. This is just the major pieces. There's a fair bit more, especially in terms of QA. But basically, once you check everything in and the source code in, and you do the integration and all the testing, you produce artifacts that were then pulled and put into an artifact repo, and then pulled out and deployed into the operational system. Now, all of this, again, was the operational system is Aether, of course. So all of this was built using open source components. And just to focus specifically, the artifacts that I'm talking about are containers and Helm charts that define how those containers are deployed. The continuous deployment system was a combination of Terraform and Rancher. And that's a fairly sophisticated bit of machinery, again, open source, but we had a fairly sophisticated operational and complex operational cloud that we were controlling. We had multiple sites. You needed to scale up the deployment. So while Aether was part of the Pronto project over the last 3+ years, if you wanted to participate in Aether, you went to the Aether managed service, which had an ops team, and you said, I would like to bring up a site. And that happened a few times. Like any managed service, the operator was doing all of the heavy lifting there. But as a consequence of that, if you wanted to stand up Aether on your own, then it was a little bit of a challenge because you didn't have all the insider knowledge that the operators at ONF had. So imagine you are here and you want to operate and deploy your own version of Aether. So let's call it My Aether. Now, this is your own deployment, but you would like to take advantage of all the same things that other Aether, the global Aether, was supporting. Well, this was a really tall order. It was possible because the code was all checked in, source code was all checked into Garrett and GitHub, but it's not an easy thing to do. It's actually quite heavy lift. And so what we have been doing recently is refactoring how the deployment into this works and gone to some slightly simpler tooling that has plenty of headroom on it, but we've changed to Ansible. And we're using this as a way of helping people to deploy their own version of Aether. I'm just calling it My Aether here. And this collectively then is something that we're calling Aether OnRamp. So it takes the same artifacts being produced by the CI end of the pipeline, checking them out of those repos. You're now able to put into the config file information about your deployment, and the Ansible playbooks then act on that. And it's your copy of those playbooks, so you can modify all the variables and so on over time. This is something that is still in a fairly early stage, but it's been done over the last 6 months, in particular, focusing on the conversion to Ansible in the last, over the summer, in collaboration with 2 colleagues, Blah and Shabazz at Purdue. They have been using SD Core in their research and had some nice machinery in place to help them quickly iterate and do deployments that accelerated their research. And it seemed to be a good thing to do on behalf of the community at large. And so we're now making this available, and it's called Aether OnRamp. And let me just sort of jump to some bullets that kind of summarize what that's about. So the main takeaway here is we're transitioning Aether from a managed service to a deployable platform. It includes still all the tooling you need to run it so that you can run it as a managed service, but you don't depend on us running it as a managed server on your behalf. The overriding goal, this is subtle, but it critically important, is to support users owning the configuration. So at one end of the spectrum, we could have provided a system that you just push a button and it deploys it for you, but that's not going to allow you to grow the system and customize it towards your purposes. So the goal here was to lower the barrier to bringing Aether up, but do it in a way that allowed you to take ownership of how it was deployed so that you could then grow it for your own purposes over time. And it's being used, that lower the barrier is being used in education. There's coursework at UMass that Jim Croce's working on. It's being used in research in a number of places. I mentioned the Purdue research. There's research at Princeton, Cornell, Intel Labs, all using this. There are some field trials that are in early stage discussion, not far enough along to really talk about, and there are also commercial deployments that have been using Aether for a while now. So that's the big transition that's underway. The other key thing here is that in addition to allowing you to take ownership of your own configuration, OnRamp is designed to scale up to different target environments. So you can start with a single server. In fact, that single server could be a virtual machine. And then you can attach both emulated and physical RANs to it. And we have done both. You can then grow from a single server to a cluster, and you do that because you wanted to scale up some aspect of what was running at the edge. And again, that works with both emulated and physical Gnode Bs. I've grayed out multi-site hybrid deployment. That's the ultimate objective for Aether OnRamp, that we get you all the way to the full glory of what Aether was able to do. That's still future work, but running a cluster at a single site right now is quite doable. And we're doing it. Another important aspect of this is that OnRamp is designed so that others can contribute back to it. It is easy to not easy. Once you take the code and then start making it your own, there's a bunch of features that still need to be added back in. And doing that, we wanted to make it easy for people to contribute that back in. So this is done mechanistically through a combination of mechanisms. First of all, the major subsystems are all their own Git repos, and then Aether OnRamp treats them all as submodules. So if you go to GitHub, you'll find Aether Kubernetes. That's the Kubernetes the platform subsystem. And I don't explicitly have this in my bullets, but it does not include the fabric today. It could in the future, but it does not include the SDN fabric today, just regular switches. The 5G core, that's SD core. The GNB SIM, AMP, that's a combination of monitoring, the closed loop control pieces, monitoring, and the API. And I'm showing Aether SD-RAN in blue just to highlight that that was not part of the original release, but that is work that is currently underway. So everything going on in the SD-RAN will be available as part of Aether OnRamp in the near future. So that's the first level of modularity. And just as an example, if someone wanted to add a UE RAN sim or some other simulator, that would be easily packaged as its own Git repo and then imported into the rest of the system optionally if you wanted to. The second modularity aspect here is, of course, Ansible supports multiple roles. So just using the 5G core as an example, there's a role to actually bring up the core. That's the Kubernetes workload. There's a role to bring up the routing that's necessary to connect the RAN to the core. Non-trivial, actually quite complicated. There are other ways of doing that. If someone offered up another way of doing that, we could just plug that as an alternative role as part of the 5GC repo. And just as an illustrated example, there's actually a branch in GitHub right now. Most of the work is done, but we've just not we've not merged it into master yet to bring up multiple UPFs. But again, from a modularity point of view, that's just another role that fits in cleanly. So I easily imagine other roles here. For example, the next one that we probably want to do is to bring up the core with SRIOV so we can improve the throughput of the UPF, but that's easily modular in OnRamp. The final layer of modularity is how all of this gets, let me say, packaged together into a set of features or a set of components. And here, Ansible var files and template rewriting is a critical part of that. So if you're not familiar with Ansible, you define a set of variables that then get it config time substituted into templates. And I'm actually going to pull out of the slide deck here in just a second and show this to you. But we've built so far the following set of call them blueprints or profiles. Each of them defines a way of deploying Aether. So now, at the risk of messing up, let me try to jump into just a little bit of the code. We plan to do a tutorial at somewhere down the line, but just to give you a sense, this is the Open Networking Lab / Aether OnRamp repo. I'm in the vars directory, and you'll see this set of optional variable files. So just to pick one, for example, main GNB, which you would substitute for main if you wanted to bring up a blueprint for Aether that included a physical gnode B. And just to give you a sense, it's basically you're specifying all of the version parameters for various components. You specify it for Kubernetes. You specify it for the core. One of the other things that you specify is the value override files. This particular one, radio 5G values.yaml, happens to be constructed to make it easy to bring up a radio as opposed to a simulator. And then you bring up AMP, and again, there's a couple of other config files. So obviously this isn't enough to understand it, but the point here is that the documentation explains how you take ownership of each one of these variables so that you can customize it for your deployment. And I'm just showing you this particular one. The other thing I would like to show you is Aether's actually running now. And this is the monitoring window. I have a physical G-Node-B. I'll show it to you in a minute. At this moment, I have running UPF. I have exactly one cell phone connected to it. This one right here, which I just unplugged, and hopefully the battery will continue on it. And let me just run a speed test on it. So this is over the last 15 minutes. Let me just bring that down to 5. And yeah, I'm not getting, I get it, it's variable. I'm not getting great throughput through it now. I'm just getting 5 megabits down. I usually get somewhere closer to between 15 and 20, and then I get 10 up. So not the greatest performance at the moment, but this has basically been running continuously now for some time. In fact, let me just show it to you since it's right here. This is the GUI. We're using the Sericom /Mozo Labs. I'll explain that in a second. Physical G-Node-B, femtocell, it runs indoors. This one's been running for 10 days, 10 plus days. It basically is showing you status as it comes up. You eventually get to the status you want, which is the radio is running. And finally, this is a physical server that has the core, SD core running on it, the 5G SD core. And yeah, it's been running for 14 days here now too. So yeah, so this is all, the way I like to explain it is it's not trivial, but if I can do it, you can do it. And it takes a little bit of work, but it's entirely possible to bring up a core, bring up a physical radio, connect a cell phone to it, and start running 5G workloads over it. Connected to the internet. When I run the speed test, I'm testing against servers out in the internet. So let me jump back into the slide deck for a second. I got a couple more points to make. First of all, one of the design decisions we made is to treat the RAN as external to the core. If you're familiar with the SD core, it had a GNB SIM as a container running inside of the core. But this means that the core interacts with the simulator in a different way than it interacts with a physical G-Node-B. And we wanted those to look the same because it's easier to debug if you're testing against a simulator that you know how it's supposed to behave versus one of these small cells that are quite fickle in how you get them configured. So by pulling out the GNB SIM, first of all, it now connects to the core in exactly the same way a physical G-Node-B does, which is good. But secondly, we can now scale up independently the workload we put in this. So you can now deploy multiple servers, each of which is running multiple containers. Each container is generating control plane workloads that run against the core. And then, of course, you can also scale up the core. And like I said, an important bit of research that's going on right now is how to scale up the AMF, and you need to scale the workload to do that, because what you're really concerned about is low latency response to IoT devices, and you may have a scalable number of those. So this is the sort of depicting what it looks like when you deploy GNB SIM. And by the way, I'm not showing it here, but there's a way to modify the simulator described in the documentation so that when I bring up an emulated UE, it actually connects to the outside world. So you can verify that you do have an end-to-end path, which is really helpful when you're trying to bring up the same thing, but with now a physical G-Node-B. So you've got a physical UE connected to a physical small cell. The networking through here is not trivial, because you're going into and out of a Kubernetes cluster, and you're overlaying, you're building overlays on overlays here. But the important thing is, if you brought up the simulator first, then once you do this, you've probably got the end-to-end path debug. This is the end-to-end path I was showing you a minute ago. Yeah, I'm going to just running the internet test again. Now I'm getting 15, 16, 17 megabits a second download. This is the small cell. as you may recall from a minute ago when I brought up the GUI, it said Seracom. It's still Seracom. Mozo Labs is the interface to acquire these. I don't entirely understand the business relationship between Mozo Labs and Seracom, but it's now technically branded Mozo Labs, and you can go to the ONF website and you can find links to both documentation for this device and a data sheet to know exactly what you want to order. This is still not dead simple. One of the things, just as an example, that we've just been working through is that you can get this with serving different frequencies. And so I had a Seracom small cell that was frequency band in 78, and this one is in 48. So it took some adjustment. Different UEs work with different bands. Different UEs are open or not open. So it's just something to be aware of. And that naturally then is a good transition to the information you can go take a look at to get started yourself. The code is on the Open Networking Lab GitHub site. Start with Aether OnRamp, but the other repos are there and they get pulled in as submodules. The guide is available at docs.etherproject.org. Think of it as more of a tutorial. It takes you step by step through the process. I know for a lot of people, you know this stuff forwards and backwards, and so you jump straight ahead to what you want to do. But my experience is if you start at the beginning and work your way through, then you have effectively done all the incremental debugging steps that you need to do to get this thing running end to end. It's not dead simple. There's a lot of moving parts that have to be coordinated. There's a Slack channel dedicated specifically to OnRamp. It's a good place to go ask questions, and there's links on that channel to different bits of information that will be helpful. And there's a roadmap, which I will conclude with in just a second. We'll come back to that. Aether, of course, is also the larger project. It has its own website, its own wiki, and the TST meets on Tuesdays, 10 o'clock Pacific time. The wiki has links to the calendar and Zoom meetings and agenda and all of that. So I encourage you, if you want to be active in this, to start to attend the TST meetings. They're also recorded. And finally, there's also background reading. These are 3 books that I have done with Bruce Davey and other domain experts, all highly inspired by Aether. So you can kind of view them as architectural, conceptual background to fill in all the cracks in your understanding behind the code. And so let me just conclude, and then we'll see what the questions look like by jumping back into GitHub and just go to the wiki. Basically, OnRamp is still early stage. You can use it. You can bring up the simulator. You can bring up GNodeBs. You can do the things I've just described. There's more to do. Support for multiple UPFs and slices, that's in progress. Support for use SRIOV, not in progress exactly, but it should be a pretty small incremental step as well. And this is all the low-hanging fruit that we would hope to have going pretty soon. If you're jumping in at kind of another level, we're trying to configure SD-RAN and integrate it with the core. That's work that's in progress. Maybe we want to bring up other simulators. We need to grow the number of base stations. Should be pretty straightforward, adding security. So I just draw attention to the fact that there's plenty of other things that if people want to start contributing, that would be great. Longer term, I think one of the biggest things is to get all the way to the full Aether. That means multiple control planes and configured multiple sites under centralized control. That's still not done. And the other big thing is we need to add more RAN options. We've got GNB Sim, which is really a simulator to test the control, the core, not to test the RAN elements. And then the physical GNodeB, but there's plenty of other options that we would like to bring in under the OnRamp umbrella. So you get this whole thing end to end. And with that, I think I will stop the sharing and go see what I have in terms of QA. Is SD-RAN dependent on Intel FlexRAN? No, it is not. It's independent of FlexRAN. And then there's a follow-on question about what DUs and RUs it supports. And the answer is the Radisys examples are ones that run in the Berlin trial. If you go to the SDRAN website right now, you'll find some examples that have been demonstrated. In my view, this is still a bit scattered and hard to deal with. A lot of it is still 4G. What OnRamp is really focused on is how to get some really concrete examples of 5G devices in here, but that's still more in front of us than anything else. So then there's another question about MZ, IMSI, IMEI pairings and locking. There's not preventing a stolen SIM card from being used by a malicious ME. There's not a lot of that sort of security built into Aether right now. So yeah, that sounds like work that would be still good to do at some point, but it's not really there. Can Aether be stood up on-prem? GCP Anthos on bare metal deployment. Yeah, these are all possibilities. At one time, Aether did run on Anthos, but in terms of what's of all the things that the Aether project did, some of them are one-offs. And what I'm hoping happens with OnRamp is we figure out which one of those were just interesting demos, fine, but which ones are useful for people going forward, and then bring those back in to OnRamp so that others can take advantage of it. And yeah, there's plenty of room there. And basically what you find that works today is all that works today. And we need to grow that set. And in particular, I would, because it's important that we have end-to-end programmability, that we have software-defined radios as part of this, is also important. And so we're looking at SRS RAN as a possibility that has been integrated with SD-RAN. So it is an option, but we've not yet made it readily available. And again, I'm repeating myself, but there's a big difference between someone did it somewhere once, and it's become part of the package that it's easy for everybody to download and take advantage of. All of these things are possible. The interfaces are standard. You can certainly do it, but it's a matter of making it easy for others to do it. There's still, from the Onos RIC point of view, kind of paraphrasing the question a little bit here, but from the Onos RIC point of view, the Onos RIC is fairly solid. Certainly the models are going to change, and the RIC needs to change to account for those differences. But most of the work that's yet to be done are building different XApps. And again, that's bringing your customization to it. And we need to have an example set in what we distribute, so you've got something to start with. But at the moment, there is not this broad collection of every XApp known to man available. What UEs are you testing? The UE that I'm running is a Moto G 5G. Pixel 7 is said to run. I've used a Pixel 4, but that was with N78. I haven't got the Pixel 4 doesn't work with N48. That N48, N78 is, as I understand, the industry is sort of gravitating towards 48, and there's a lot of devices out there that aren't configured for that yet. Yeah, other questions about SD-RAN, can we use USRPs? Yes, that's been done. That, again, that can continue, and you can go off and do that. What I really would encourage people to do is find a way to do that and then make it available here so that it's more widely available. There is USRP support. It has been demonstrated as part of SD-RAN. It's not yet part of OnRamp. Okay. So I think There's no split. Yeah, the Mosel Lab Sericom device I'm running right now is not split ran. So I think with that, if you have more questions, go to the Aether. If there's sort of development questions about the innards of SD core SD-RAN, then there's an Aether dev and an SD-RAN dev. That would be a good place to ask those. If it has to do with how do I bring up all of this stuff and run it, then there's an Aether OnRamp channel that's good for that. And so with that, I think I will conclude. And Denise, is there any close-up work to do?
Well, thank you, Larry. Thank you so much for your presentation today. And thank you to everyone that joined as well. Following this webinar, we'll send you an email that includes the video recording of the meeting, as well as a copy of the slides and information on how to access Aether resources, many of which you've heard about today. This concludes our broadcast today. Thank you.